It's obviously, we're a little late in getting the video stream set up, but hopefully people are there. I've got a few things to give away, which were handed to me yesterday. Firstly, does anyone remember who won the mouse and mousepad at the quiz night? Was it Mark or... I'm looking at you, Daniel, because you were there.
I was there, but I don't remember.
I can't remember. Anyway, I've got that now to give to whoever's there. But I also have a T-shirt with a penguin on it. Who'd like it?
Yoink.
Oh! I think I saw your hand go first.
Oh.
Right.
There's no one committee, so he gets priority anyway.
Next up is a pair of mugs. Can I have an assistant? Would you like to open that?
No worries.
And Bill, could you open that one? They are different. And of course this is going to leave lovely polystyrene foam over the IBM floor. Right. So, one of them is a Debian mug. And the second one, which Bill is delicately opening. Can we get some photos of your place at Christmas time? I'd just like to see what... Fear the Penguin, it says. So this is from Scott Middleton. Who would like the Debian mug? Done. There you go. And who would like the Fear the Penguin mug? Done. I saw this one first. There you go. Would you like the box as well? Grab it afterwards. So the other news, obviously, from the last month since we had our meeting down in Fremantle, obviously, is the talk that we've got scheduled for October 11, which Daniel is organising, where we're going to be flying Rusty Russell over from Adelaide to come talk to us for the evening.
The second Tuesday?
That is the second Tuesday of October, the normal scheduled time slot. Bugger, my phone. Oh, good. So, obviously we're doing that by splitting the cost between everybody who's going to be coming along, $20 a head for members, and obviously we've put that to $50 for non-members, and obviously until the end of this month, membership $10. But we'll have a fun night with Rusty, and I think we're probably going to do also a panel, as well as a talk, to get people up and discussion happening. So, if you've got your $20, please let Daniel have it, as it were. What other news have we got from the last month? I listed a whole heap of stuff on the Plug website. Daniel's quickly looking it up. I just think we haven't got anyone else from committee here tonight, other than Daniel and Alistair. Mark Gaynell's not here. Nick Bannon is still in Ireland. Jason Nichols was unable to make it.
Peter Lyons is in Melbourne.
Peter Lyons is in Melbourne. Though we do have some Susie DVDs, which I think are at his house at the moment.
No, they're not.
No? Where are they?
They're in a bag.
You have them here?
Yes.
Excellent. Would you like to give your news?
All right, I'll go get the bag.
Go get your bag.
Your other news is the membership fee increase, meeting start times, member section is operational again.
Yes.
Server, Icecast server, Urban Terror, and people are on.
I'll try and expand on those if I can remember them. So the members section of the website, if you've got preferences for where your email for Plug.org.au email addresses, And the member server will be coming back shortly. Alistair, you can talk about that in a second. We have CDs. Here, you do.
Would anybody like an OpenSUSE 11.4 DVD? OpenSUSE is actually a moderately good system. It doesn't do crazy stuff like Mandriva, and it's probably the second most popular, or third most popular after Debian and Red Hat. It's worth a try if you've got a spare system you'd like to try and boot. I'll be chatting to you later.
Just for fun.
All right. There you go. You want one? There you go.
It takes all the trickiness of Debian and gets rid of it. Which is mostly the people.
All right. That's it for me.
Cool. Lovely. So once again, just a reminder that membership fees going up to $20 at the end of this month. It's the first increase of Plug membership fees since Plug was started some 10, 11, 15 years ago. To help cover the operational costs of being an incorporated association and also to be able to do interesting things. Logo competition, I just suddenly thought, was being run by Mr. Bowden at the back of the room there. We have 2 entries. We need to have a chat to see whether or not we go for another plug or whether we choose a winner.
I think what we need to do is to now publish them, which I'll try and do late tonight.
Right.
And then invite people to work on those to get the vector format.
So let me re-say that so the people who are listening on the stream can hear. Can you tell me how many people are listening? How many people are connected to the stream? 2, 3?
It's gone viral.
5?
Current listeners, well, it's saying 0, peak listeners 0, but I don't believe that's true. According to Tim White, there's 2 people listening.
Yay. Okay. So
It's crashed for a while though, stream.
Right. So as Tim was saying just then about the logo competition, he's going to publish out the current entrants that we've got. Obviously, we were after these in vector format so that we can blow them up and shrink them down. We'll get some posters made up, potentially by the time we've got the next meeting. But Tim's suggesting that we publish these out, the current entrants, and let people tweak them if they want to improve them. There's still time if you want to put an entry in. Inkscape is one tool you could use to produce vector graphics. So feel free to send something in. Every real legitimate entry gets a free here's membership to Plug. So if you want to just
that includes tweaking someone else's entry.
Yeah, we're desperate for ideas, and I don't have an artistic bone in my body.
Yeah.
Autistic, maybe, but not artistic. Okay. Anyone got any other news? In which case?
We're also going to have the wallpaper published on the website, which I was meaning to do a while back.
Oh yes, the wallpaper.
But if anyone else wants to contribute any wallpaper, that can also go up on the website. I'll do that tonight as well.
Cool. In which case, let me introduce our speaker then for tonight. And I will do the quick shuffle with the radio mic so the guys at home can see. Indulus Bernstein has worked for IBM for
Years, 20 plus years.
Plus years. Mm-hmm. Do you get a special award?
Yeah.
Or commiserations?
Yeah, exactly. No, you get free treatment.
Free treatment. Oh, nice. Probably need that after that. Indulus has been in the IT scene here in Perth long before that, having come out of UWA, following in the footsteps of those of us that survived the UCC and computer science there. I'll do the shuffle over onto the radio mic and let you take it from there. Thank you very much for giving us a talk. Please give him a round of applause.
Okay. Well, you'll get the dubious pleasure of seeing me rarely now in my tie and my formal attire. So I also thought it was suspicious that it actually stopped on a NORAD view of one of the NORAD screens with the missile heading towards the USA. But anyway, we're just showing a video of IBM over the last 100 years because IBM is 100 years old this year. So let's go back to the main presentation. Punch cards, people with strange haircuts, etc., etc. So, let us begin our talk. So, welcome to everyone. And so I'm just going to do tonight just sort of a bit of a cook's tour. I used to do like my history in IBM, I started off working with PCs in 1982, so just after the PCs were, Intel IBM PC was first announced. At the same time, I was a mainframe systems engineer as well, and then in the late 80s, I actually moved into Unix systems, and then stuck in Unix systems from there until probably around 2005, 2004, and then basically changed over to being a cross-platform systems engineer or systems architect. And about 2 years ago, I moved from designing large commercial systems to run, database backends for banks and retailers and stuff, into the much more satisfying and geeky high performance computing area, which has been great, and has also meant basically learning a lot about a lot, and pretty much having to cover most of IBM's product range apart from mainframes and mainframe disk storage. So tonight what I thought I'd do is go through, I don't know, just cover a little bit of sort of history of IBM and some of the sort of significant inventions and things. And for those of you, as you came in, you would have seen the video of Watson playing on Jeopardy, and so I thought I'd also talk about Watson and cover some of the technologies that are involved. So I deal mainly with servers and storage, so they're my focus areas, and if you're interested in that type of thing, great. If not, well, I'm really sorry that you're here tonight. All right, so let me hopefully remember which way this goes. Not that way. Okay, so history of IBM. So IBM started off as Daytona Scale Company. You can see a lovely scale on the right. Some nice old-fashioned logos. Then turned into the CTR, Computer Tabulator Recording Company. And IBM's also manufactured a weird assortment of devices, such as meat choppers, also manufactured rifles during the Second World War. So there's some very strange things that IBM's manufactured, not just in the computer sphere. And then in 1924, renamed IBM, International Business Machines, with the really classy, lovely logo, which then changed into starting to look a bit more computery, more nicely blocky 1956, and then the logo that everyone knows, the striped logo of IBM. IBM did have a songbook in the early days. There was actually a corporate songbook, and there were songs written for vice presidents' birthdays, etc. So fortunately, we've never had to sing one of these in any of our meetings. So I'm probably fortunate for the people listening, as well as fortunate for the people singing. I don't think so, but I can probably do better than that. I can actually.
Page 5 of the songbook will do one verse and two choruses of ever onward on page 5 of the songbook. There's a brilliant star below the weir about the soul, the longer age, the longer in the land. We're here to purify and hear and all the godly laws, all that land of man our friend is dying, and the name of DJ was the nation very not to them, and we feel honored to be here because we are very sorry.
I think that's probably enough of that. And so it goes on, and stopped on Ronald Reagan looking at some computer system. Okay, I recently went to the IBM Almaden Research Lab, which is the home of storage research, as well as some basic physics research. And in fact, I was able to go to meet the guys that actually invented the scanning tunneling microscope, which is capable of not only giving a visual of materials down to the atomic level, but it's actually also capable of moving individual atoms around. And one of the things they do is, if we take customers there, they actually let them go on the joystick and actually move an atom around and place it. So we actually saw in the lab this machine, the RAMAC, which is the original disk drive, which was invented in 1956 with a total of 5 megabytes of storage. Who would ever need more than 5 megabytes in the whole world? But we also sourced the Spintronics lab, which was basically a lab about the size of this room, filled with stainless steel devices, pipes, pumps, etc. And they're doing materials research for the next generation of storage. And the idea is, if any of you have been around for long enough, if you remember magnetic bubble memory, something sort of similar to that, except that it uses things that look like little tuning forks, and they actually move the domains up and down the tuning forks and use silicon sensors to actually sense the magnetic domains as they go past. So effectively, we're talking about solid state magnetic storage, and the nice thing about it is the fact that when it's manufactured, it'll be manufactured sort of with hundreds or thousands of these little tuning forks, each of which may contain a fairly small number of bytes, but we'll be able to have massive throughput because of the parallelism. So that's quite interesting to be there. And apparently the two labs, they're right next to each other. They have this rivalry between them about who's going to, try and win the next Nobel Prize, right, in physics. So I guess that's one of the nice things about working for IBM. It's actually probably the only computer company left that actually does basic research through from silicon through servers to software and services, and we pretty much cover it end to end. So if you buy chips today that are manufactured using silicon on copper, that's an IBM process. Silicon insulator, that's an IBM process invented by physicists at IBM, and most of that materials work happens at the Almaden lab. They also developed GPFS parallel file system, which we use in the HPC area, and we'll be talking about that a bit later. So, and in the foyer, they've got one of these. So I actually saw one in real life.
Operational?
No. Okay, so 1962, 2311 I think this was, but well before my time. But now we've gone up to 7 megabytes, and now it's a removable pack. Very modern. You'll notice the modern screen here with the graphics display, vector graphics display there. 1999. This was pretty amazing in 1999 to actually have basically an SD card, a compact flash card size drive. So that was actually a hard drive packaged in there. I remember I actually got one through nefarious means inside IBM and was using it in my camera at the time when most memory cards were of the order of 16, 32 and 64 megabytes. And for those of you who don't know, IBM actually invented the Winchester disk technology as well. That's used in all of the disk drives today. Sorry. And of course now in 2011 we're talking about petabytes of storage. Change in actual logic circuitry from 1955. This system, I don't even know what system it is, like no, it's not a 704, it's later than that. 3,000 transistors. And today we've got a Power 7 chip which has 1.2 billion transistors, and because of some of the latest advances in shrinking memory cells on silicon, this is actually equivalent to 2.7 billion transistors if you manufacture this using normal processors. So this enables this Power 7 chip to have 8 cores and 32 megabytes of level 3 cache per core as well. So it's a pretty impressive achievement. So this is, and as a summary, IBM researchers have won Nobel Prizes, Medals of Science, 22 members in the US National Academy of Science, 6 Turing Awards, 10 inventors in National Inventors Hall of Fame. And we just have a look through up here, things like that's solid state disk drive, RAMAC, Fortran, fractals, relational database, the one device memory cell, otherwise known as dynamic RAM, Winchester disk, thin film recording heads, RISC, high temperature superconductivity, as well as STM. And as we go through here, you can see up the top, the world's first petaflop supercomputer, which was the Roadrunner system, which was based on a combination of AMD processors and cell chips. So basically the same processor that's in a Sony PS3 PlayStation.
I was just going to ask that, yeah.
The millipede was this idea that it would actually crawl along and actually do sensing. So it was actually like a mechanical device. The idea was that it would actually sense sense different changes in, I think it was polarization. So they actually it could heat up cells and they could detect the polarization of the surface layer or something like that. But it was basically a storage device. So that was the idea. I don't think it ever went anywhere because, as with a lot of these things, it's not just inventing the technology, but you also have to gear up to be able to manufacture it. And so in the 1960s, before CMOS became the dominant manufacturing technology for chips, the competing one was a thing called ECL, emitter coupled logic, which took a lot more power. Now IBM invented a superconducting semiconductor, which was very low power and had very high switching speeds, called the Josephson junction, and then spent about 10 years or 15 years trying to manufacture it and to actually, manufacture chips based on this technology. And that while they could actually get individual devices to work, it was never capable of being scaled up to chip level. So that was eventually ditched. So that was one of those inventions that went nowhere. So it's not just a matter of inventing it, but sometimes things don't get from the invention stage to the wide-scale manufacturing stage, or something else takes over. So like NAND memory, flash memory might have taken over in terms of price, performance, and density. And what's the point of trying to manufacture something when there's another device out there that does the job adequately for a similar price? Okay, so I was talking before about the DRAM technology, so I just thought I'd delve into one of those inventions. So on the Power 7 chip, the way they get the increase in the amount of memory that's on the chip is to use eDRAM technology. Basically, DRAM typically is slower than static RAM, but eDRAM is almost the speed of static RAM, more reliable than static RAM, and takes up less silicon real estate than static RAM. So it's a win all around in terms of putting this on devices. And it means you can get much better level 3 cache performance. And if you ever deal with when you're designing a complete system, you have to have sort of a hierarchy of cache, which sort of starts off at the disk, maybe goes through SSD, then goes through adapter caches, main memory, level 3, level 2, level 1, and then into registers inside the processor chips. So, if you can actually make that level 3 cache more effective by making it faster and making it bigger, then you can save a lot of time going out to main memory, because you're talking about orders of magnitude difference in access time between internal cache and main memory. And in this case, because the level 3 cache is on chip rather than external, you don't have to go out through buffers and drivers and drive bits of wire, which is the thing that actually slows processes down. Once you actually get off chip, that's when things really slow down. Yeah. And in terms of innovations, IBM, I think it's the last 16 years, has been the leader in number of patents, with Microsoft a distant second. And this includes sort of software patents, services patents, as well as hardware patents. And let's not go into a discussion about software patents. Thank you.
With that claim you've made, to what extent do you consider a number of patents to be actually a measure of innovation?
Right. I think that's an over a beer discussion, but certainly a lot of them are, right? And IBM's actually donated patents to the Open Source Foundation as well. So it's not like we just take the patents and we just lock everything up. Unfortunately, the way that patent law works in the US at the moment is that you have to have a patent portfolio purely as a defensive mechanism and as something to trade with other people who say that you're using their patents. So there's this trading and in fact, the NORAD picture, the idea of mutually assured destruction. If two companies with patent portfolios go after each other for too long and too hard, and the patent portfolios are reasonably equal, that's what keeps the detente and the Cold War running. And then I thought we'd now sort of go from the history into the area that I work in, which is the supercomputer area. And these are last year's supercomputer figures from IDC, showing the split up between between the different vendors in the supercomputer market, the deep computing HPC market, and you can see that HP and IBM sort of fight it out with Dell a distant third. But it's interesting when you actually look at how that's composed. So the green bars here are showing you the systems that are worth more than $500,000 US, which says that basically IBM is really good at building really big systems, and not many other of the vendors are, and we sell quite a lot of them. But some of the other vendors are actually better at departmental, smaller HPC systems, and have more market traction in that area. So consequently, when you hear about IBM in the supercomputer segment, it is at the high end, because there's a lot of work that's done with the US government. In fact, that drives a lot of the innovation in our power-based systems. One of which was actually used for Watson. So. Which leads me into Watson. So I thought we'd sort of divert a bit out of supercomputers and use Watson as an example of something that's interesting and leading edge. And as you came in, you would have seen, how many of you here have actually heard about Watson? Everyone. Okay, right. So for those of you who are on the web, everyone raise their hands. So I'll at least say that Watson is really designed to try and promote the ability to analyse very large amounts of data and produce coherent, good guesses or at the meaning of questions, and actually come up with reasonable outcomes from that natural language query. And so it's a very hard task, even for human beings, to actually be able to play Jeopardy and win, because the clues are really difficult and the answers are not always obvious, and they're obscure, and they use puns and all sorts of stuff. So the idea was that they'd actually use Watson as a research project to drive forward technology. And you'll see some of the other technology that we talk about later also came through from basically, somebody in IBM saying, hey, this would be a really good project to drive the technology forward. And another example is the Blue Gene set of systems, which I also deal with, and which you'll see some examples of later, which was really designed initially just to do protein folding, but since then has been through a couple of generations, and now is much more a general purpose system with an exceptionally good performance per amount of power that you feed into it. So Watson integrates Power 7 processors, SLES Linux, and also IBM's Deep QA software, and 15 terabytes of in-memory database to actually answer, to both analyse the question, come up with an answering strategy, and then actually produce what's hopefully is a correct answer in under 3 seconds. So the way it's physically set up, it's 90 commercially available Power 750 servers, and they're 32 core servers, 2,880 Power 7 cores, 500 gigabytes per second is the on-chip memory bandwidth of each of those. So you divide that by 8 and you'll get so it's 400 times 500 gigabytes, about 200 terabytes a second of main memory throughput. 20 terabytes of disk to hold the database, plus 15 terabytes of memory to actually hold it when it's actually running. And UIMA is a standard which IBM has developed, and again given to the open source community as a standard way to mark up and to present unstructured data. How you do that, I don't know. Don't ask me. I'm not a software guy, right? I only just started looking at this UIMA because a few years ago I got interested in semantic web, and I started reading up on it. And I think this is the outcome of some of that semantic web of how to classify unstructured data in a way that you can actually retrieve it and maybe even make some sense out of it. Well, obviously it does. And so it's 10 racks. And I thought I'd actually go through, before we go into that, is to actually look at a short video which shows you a little bit about the actual system itself.
enormous amount of science involved when
Hopefully
Watson
people
answers
will-
a single Jeopardy question.
Watson, what is polka? That is correct.
There's natural language processing. There's machine learning. There's knowledge representation and reasoning. There's deep analytics. And it all happens in just 3 seconds.
What is South Dakota? That is correct.
The computation that Watson's performing is what we call embarrassingly parallel, which means that lots of different threads, different computations are triggered all at the same time.
If you try to run Watson on a single processor, it would take a couple of hours for each question. But IBM had to create a new computing infrastructure that would allow them to do lots of parallel distributed computing to really bring down the time required to answer a question.
So we set about building an optimized system. I use the word system because it's really a combination of hardware and software.
That application is the key. Start with that. What are the key requirements for that and how they need to be satisfied? You bring the elements that are required to take care of that application need.
We ended up using one of IBM's high-performance computing platforms, one that scales very well, meaning it can run massively parallel computations. And this was the Power 7 platform. It has many, many CPUs, all densely packed together, sharing memory.
Most importantly, and one of the biggest things that separates Power 7 is bandwidth. Watson, for example, has to access terabytes and terabytes of data to answer a question. Our processor has 500 gigabytes a second of capability. Most other processors are down below 200.
The Power 7 system is tuned for very rapid, deep analytics of massively parallel problems.
Anytime you have to address a very specific task, you're going to have to bring together both software and hardware to create a highly optimized system. From the ground up, from the chips right through the software stack for addressing the needs for that application.
We believe that more and more systems will be designed for specific tasks to execute particular kinds of workloads. Watson is that. It is obviously tuned for a very particular kind of workload called a Jeopardy.
Watson wins the game. Very well played, though.
Watson is the culmination of a long commitment to speech recognition, large data analytics, supercomputing, all coming together at this point in time. We knew if we could get this to work on a commercial system, the rollout into other fields of deep Q&A would be greatly accelerated. We were going to revolutionize industries at a level which has never been done before.
I think that's pretty interesting as a research project. So the aim is there are some more videos. Go away now. So there are some more videos on YouTube if you're interested. I'm talking about Watson being used as a natural language interface for medical, like medicine, so that doctors can actually ask questions based on symptoms and actually receive different receive answers. And you'll see later on. I'm not sure if it's in this video or another one. Oh, sorry. But Watson actually comes up with a number of different answers as it trawls through and actually tries to figure out which ones are the most probable based on its analysis of the database. And then obviously in Jeopardy it chooses the most likely one, and it has for Jeopardy it has thresholds set. But the potential is that you could have somebody present to a doctor. The symptoms are typed in, and then you actually get a list of different diagnoses that may be applicable. So one may have a probability of 20%, another 25%, another one 12%. It doesn't mean that the system's going to be able to actually say what the correct diagnosis is, but it'll at least be able to give some clues, and particularly because it's able to trawl the web and be able to digest the latest information, which as human beings we just don't have the time to do. So you're really relying on human beings to doing what they're best at, with observational skills, interacting with other human beings, and you're relying on a system which can actually supplement your knowledge with the latest knowledge that it gains from trawling other databases for information. So this just shows, and you'll see in a minute, this just shows the sort of Jeopardy graph, which shows how confident the humans were in terms of the number of questions that were answered. In other words, how confident a human acted in a Jeopardy game and how many they answered, and saying how many questions they answered right. So, you know, we actually have quite a few ordinary players who are quite confident but don't actually answer the questions correctly, whereas the sort of masters live up in this area. And we'll see later on how Watson worked. As it was being trained, there was some spectacularly funny responses, like, you know, decades before Lincoln, Daniel Webster spoke of government made by and answerable to them. And Watson's answer was no one. So the government answerable to no one. Of course, the answer is to the people. New York Times headlines: an exclamation point was warranted for the end of this in 1918. Watson said a sentence, which is logical and probably accurate, but not what was meant. It was obviously World War I. In 1994, 25 years after this event, one participant said, "For one crowning moment, we were all creatures of the cosmic ocean." What did Watson say happened 25 years ago? The Big Bang. Maybe not. What it was actually was the Apollo 11 moon landing. The Queen's English, this is my favourite one. "Give a Brit a tinkle when you get into town and you've done this." And Watson responded, "Urinate," which again, entirely accurate, but the actual answer they were asking was a call on the phone. This Frenchman was the father of bacteriology. Watson said, "How tasty was my little Frenchman?" Whatever that means. Of course, the answer was Louis Pasteur. And there's another one that doesn't appear there, which was what grasshoppers eat. Kosher, apparently, or grasshoppers are Jewish and eat kosher food. So, so you see there was quite a bit of work done to train Watson, and we'll have a look at the end of this session. I'll stick on the video, and anyone who's interested to have a look can actually see the performance of Watson, how it actually stacked up in the real Jeopardy, and some of the weird ways it answered, and some of the programmers explaining why it answered in particularly weird ways, what seemed to us weird but actually makes sense when they're explained. So this is the way that the system works. So it parallelizes, it decomposes the question into multiple different questions, looks at hundreds of sources, hundreds of answers, parallelizes all of this, scores tens of thousands and hundreds of thousands of different potential answers through text analysis, and then actually puts them through, scores them, and gives a confidence ranking for those questions. And you'll see that if you stay around to watch the video, you can actually see there's like a little chart which shows you the different levels of confidence. Actually, maybe further down here. So this is an example where taking information from different areas can actually be used to judge, in this case, as I was saying, in medicine, as to what a diagnosis might be for a patient, considering things like, you know, the symptoms, the weighting on family history, medications, and personal history, and giving an overall confidence level. So this is how Watson progressed, and some of the answers we saw were probably from the baseline, which was only in June last year, running all the way through to November last year, just before it was actually pitted against mere humans to play Jeopardy, and you can see that it sort of started to play around in the winners area where Jeopardy winners can also exist. This just reiterates. Here's an example of the confidence. So the confidence in this was, you know, Emily Dickinson was 99% for the answer to this question. Walt Whitman was 60% and Barnard was 10%. So it basically came down to the last few hypotheses that seemed to make sense, and then ranked them according to probability. And the database is about the equivalent of 1 million books, and even up to the last minute, they were feeding in information from Wikipedia and you know, IMDb and all sorts of websites to actually train the system up with the latest in pop culture, because part of Jeopardy is there are sort of current topics as well as general knowledge. So we'll head back from Watson, well, it's a sort of interesting diversion, back into the world of supercomputers, which is what I deal with pretty much on a day-to-day basis, and looking at the peak performance numbers for computers over the years, and you can see that that's a logarithmic scale. So we're going from 100 calculations a second, going up to petaflops per second. 10 to the 15 floating point operations per second, which is quite significant, and predicting to reach, if the technology keeps advancing, 1 exaflop in 2000 and in the next decade, 2000 and teens. There are issues of which are severe, which we will talk about in terms of the challenges. Core frequencies, which we traditionally relied on to keep us going on Moore's law, ran out a couple of years ago, so we can't keep pushing out beyond probably 4 gigahertz. 3, 4, in the mid 4s is probably as much as we can do with the current semiconductor technology. And at those rates, we need about 100 million cores of processing power to deliver an exaflop, and we want to know how we're going to program that. Yeah.
Sorry, you're saying as
James.
clock speed goes, what is there an impact of reducing the nanometer scale that's being produced on? Because currently is it 42 nanometers?
It's down below that. I think it's 35. So the question James said was, is there any impact on the power, etc., on clock speed, on reducing the scale? Yes, there is, but we're getting down now to where we're talking about the actual device. Devices having tracks, etc. Yeah, the being of the order atoms, and so you can't actually squeeze it down a lot more. And the other problem is that you could, the heat goes up because you're squashing things down further. If you're asking to switch faster, it heats up. And the density, I haven't got the chart here, but basically we're well past, on a standard chip today, we're well past the heat density of a nuclear reactor, and we're well on our way to the heat density of a rocket nozzle. So that's where you're heading if you keep going down that track. And the other thing is, you can say, oh, well, let's drop the voltage, but that then causes you to have other problems, because then you get noise effects and the actual switches become everything becomes more unreliable. Manufacture also, as the scale goes down, as the scale gets smaller, the manufacturing also gets less reliable. So it's harder to actually get a working device, because the physics changes from bulk properties to individual atom properties. And even when you do get the design right, you've still got to manufacture it in bulk, and your actual yields go down, potentially as you drop down in scale. And many manufacturers have found this problem. Yeah, sorry. Next question.
I think IBM made a chip that was running 300 megahertz years ago.
300 gigahertz?
300.
So yeah, would it be 300 gigahertz? So the question is, IBM made a chip that ran at 300 gigahertz. Yeah, I think we have, but that's probably gallium arsenide or something exotic like that. So the other side of it is that you've got to keep costs down, and manufacturing gallium arsenide chips is really insanely expensive. So right now, to make silicon do what we want it to do, is to keep going is really hard just by bumping the clock speed up. So
do you have plans to go further in tasks that you cannot parallelize?
Oh, okay. So yeah, this is the next question. So how do you parallelize? Well, that's an issue which everyone's battling with at the moment, and the battle is the fact that your software has to be able to do it as well. And that's the real issue, is that some algorithms don't parallelize well. They just don't.
So do you have plans to keep going on expensive CPUs that would go very fast, or do you?
So the question, yeah, okay. So the question is, are we going to keep pushing the CPUs? Well, right now it doesn't look like we can push the boundary. Like the previous generation of power chips was at about 4.7 gigahertz was the top speed, and the current generation of Power 7, they've actually dropped it down again. And what they're doing is doing some more smarts, like with the level 3 cache. So every design of a processor chip, whether it's a GPU chip or a memory chip or a processor, you have to decide what you're going to use the silicon for. And really, on a processor chip, you decide really three things. One is the amount of silicon area that you're going to allocate to memory. The second is how much you're going to allocate to processors. And the third is how much you're going to allocate to logic that makes it easy to program and transparent to programmers. So for example, in today's RISC processors, they'll actually often execute multiple streams of instructions in parallel, so they'll reorder instructions. So if a compiler generates a set of instructions, so you're doing work on register A, and there's another set of instructions following which is only working on registers B and C, then those will actually be executed in parallel on different parts of the chip, using a thing called register renaming, so it can actually reuse and reallocate resources. So there are tricks like that you can do to continue to make it easy to program as if it was a linear set of instructions, so the hardware does the reordering. Now, one of the things that was difficult in the Itanium is that they actually chose the opposite. They said, we're going to make a machine that always executes in order, and what we're going to do is rely on compilers to actually figure out what the most oftenly used path is and actually compile it so that those instructions are in the most optimum order. And that was one of the difficulties that Intel had with that processor, was to actually make that work, because obviously if you take one path of code through when you're doing the analysis for the pre-compile work, and in reality when people are running it, they take a different path through, the performance would drop. So there are lots of different approaches, and there's I haven't seen any plans to push the frequencies out beyond that. So this sort of limit 2 to 4 gigahertz for high performance single cores, and probably in the order of 1 to 2 gigahertz for power efficient cores is really where it's going to stay, and everything else will have to be done with tricky programming and parallelism. So interesting, if you actually try to build an exaflop system based on today's chips, you'd need about 2 gigawatts of power, which that's going to set your meters spinning, right, spinning madly. And I know that IBM actually did this analysis as well, and looked at an exaflop system, and just the memory driver chips in a system that was of that size, just the driver chips, not the memory or the processors, was going to consume 26 megawatts of power, right? And so obviously I went, you know what, I think we've really got to rethink how we actually do this CPU to memory thing, and so you've seen like that EDRAM to shrink the memory down and make it more power efficient. The other thing that's happening is that memory used to be on this downward curve where the price, the amount of price per gigabyte or price per bit was actually on a downward trend, whereas now in DDR3 and DDR4 that's expected to level out, and the density is not going to be able to increase that much. So the upshot of it is it's easy to make CPUs. It's going to be much harder to put enough memory behind them and enough bandwidth between them to actually keep those CPUs busy, and that's going to be the real trick. So we're already seeing that. I'm already seeing people asking for more and more memory rather than more CPU performance. So in the future we may actually be rating our supercomputers based on just purely gigabytes or terabytes of memory rather than on the floating point, because you'll just assume you've got enough floating point to use, or processing power to actually use the memory that's in there. Network bandwidth, as the number of processors goes up, obviously you're going to have a pretty sneaky and good network built into it. And so you can see that with the IBM system, so typically out in the supercomputer area, InfiniBand is king, really, because it's 40 gigabit a connection, and the switches are inexpensive and they're very low latency. So 10 gigabit is you see it often in smaller clusters, because as the 10 gigabit switches get bigger, they actually get proportionally more expensive than the InfiniBand switches. So typically, you see 10 gig E and InfiniBand at the low to mid end, and then at the high end you'll see a lot of InfiniBand. The other thing we're seeing is going back to proprietary switch fabrics. So both the Power 7 systems, which we'll be talking about, which are coming up, and also Blue Gene actually have the network built onto the chip. So there's not an external network. Basically, the processing chip is the network. So it's very tightly coupled in, and really we see that that's the only way that we're going to get sufficient scaling, because once you start building fat trees, which have a any-to-any connectivity for a large number of nodes, it becomes tricky, expensive, and the latency starts to go up. And I/O bandwidth, yeah. So basically, you also have to balance the amount of memory to the amount of floating point performance that you have on the system. And this is one area that this is one area that GPUs in particular can run into trouble, because GPUs are stuck at the end of effectively an extremely slow PCI bus to actually load data in and out. So consequently, if you spend more time with a GPU, you can actually spend more time loading the data in and getting your results back than you actually spend computing, right? And if those operations are happening in parallel, you get to a point, and I think it was depends if it's PCI 8 or PCI X8 or a full X16 slot that you're connecting to, but it's either 140 floating point you need 140 floating point operations to basically be able to effectively overlap your load and compute effectively. So if you go below that number of floating point operations per byte per floating point number, if you go below that number, then you'll actually start to starve the GPU. And it doesn't matter if you've got an infinitely fast GPU then, because it's just sitting there twiddling its thumbs, waiting for the next delivery of raw materials. So the people in the factory are sitting back and yawning, no matter how fast they can potentially manufacture or process the raw materials, the data that's coming in. You can't actually feed the system fast enough. So consequently, GPUs are great if you can load in, if you've got an algorithm where you load stuff in, and then it sits there crunching it for a very long time in comparison with the time that it took to load the information in. But we're on an exaflop system, you've got more troubles than that, because if you're trying to do a checkpoint, it's going to take you a hell of a long time to actually read in 1 exabyte of memory if you can only ingest or save it to disk at 4 terabytes in every 15 minutes. It's going to take you weeks to actually do a checkpoint. So the era of checkpoint on these large systems and restart may actually be coming to a close, just purely because it's going to be quicker just to rerun the job than it is to try and do a checkpoint and put your money into even more computing, so that if it does happen, the job's rerun much quicker. So there are some weird things that are happening in the supercomputer market. So we've seen where it used to be a very proprietary architectures, proprietary interconnects, went through to being basically common off the shelf hardware. The level of power, level of performance you need for every watt that you put in to these systems, and the design of these systems, both from a network and memory perspective, as well as the CPU perspective, means that they're starting to become more and more bespoke and more sort of proprietary, going back towards a proprietary technology. So we really see the market in supercomputing splitting up between the common off-the-shelf sort of x86, build it yourself, stick an InfiniBand network in, to where the large systems are going to be back to being bespoke systems with very purpose-built chips, very purpose-built operating systems, and purpose-built networks to support them.
Obviously, the cost factor of the bespoke is going to continue to go down, and then the bespoke will go up.
So the comment was the bespoke cost will go up. Well, I mean, one of the things is, though, that because the systems are becoming bigger, you're starting to get economies of scale. So I'm not sure where I saw this, but I think it was on the web somewhere, where Intel, the amount of CPUs that Intel actually puts into supercomputers is something like 5 or 6% of the total production. So it's actually a really significant chunk, because these systems are big, right? And so there are economies of scale just from putting a few of them out there. And also, like within IBM, we actually leverage the development work we've done for other cores. So basically, you've got Xboxes and Wii's running power chips. You've got commercial products running power chips, and guess what? Blue Gene and the high-end Blue Waters system in the US are based on power chips. So you can actually have some reuse of technology, and the economies of scale in the commodity market then drive the customization of the core components, and you wrap a network around a power processor, and it doesn't have to be a fast power processor. It's under 1 gigahertz, the current processor chips, and you find yourself with a Blue Gene, right? So you sell a few hundred of those, and there's a market there for that type of technology. So yeah, I think there's sort of counterbalancing forces at work as well. But certainly, what you see is that the technology is also sort of driven by the commodity markets to a certain extent, where the investments in the technologies for the commodity market then allow you to customise those technologies for other products. So, a bit about energy. So we'll dive off into energy of consumption of systems. The cost of power and cool servers in the future may well equal the cost of acquisition, and we're about at that break-even point now. And the systems consume per square foot or per square metre 10 to 100 times more than a typical office building. And we had that discussion earlier on about trying to convince the architects who refitted this building that we actually needed more density in our server room than we needed 10 years ago. So you're really seeing it go up from sort of 5 kilowatts a rack to 10, and now we're talking about 30 kilowatts a rack, and you'll see that go up. That's a double width rack, so 15 kilowatts a rack, probably going up to 25 or 30 per rack at the extreme end. So we're starting to see some more exotic technologies, which we'll touch on a bit later.
Can I ask a question about
Yeah, far away.
I know Google's been doing stuff with open air data centres, or tent data centres basically, where they're using ambient air for effectively venting. What's your take on their approach?
Okay, so the question was about using ambient air for temping, for actually cooling the system. Great if you've got that luxury. The problem is that it takes, okay, so first, you've got a bunch, in the supercomputer area, you've got a bunch of big data, right? You need to process that big data. So you've got a choice. You either process it where the data lives, or you move it somewhere else. The cost of moving the data computationally and energy-wise is like an order of magnitude more than just computing where it is. So you're much better off just leaving it where it is and computing it there. So you don't have the luxury of Google, where they have a distributed system that they can put anywhere they like in the world. Often these systems have instruments that are generating the data. So you've either got machines that are doing reading genes, so gene sequences, or you may have something like the SKA radio telescope, and even the Pathfinder telescope, which is 1% of the final SKA, is capable of generating like 70 terabits a second, and you've got to catch that, process it, and yeah, if you do it in up front, you can still get that down by probably 1 or 2 orders of magnitude, but you're still talking about a lot of data that's landing on your doorstep that you've got to work on. So you've got to be there to process it. You can't pipe it to the Antarctic where you've built a data center. Let's not even think about global warming and what that's going to do to your plans for cooling, for free cooling. So I think for some things it's great, and we're talking with a few of our customers about some more exotic cooling technologies, but certainly water cooling is really where it's at, and we'll actually touch on where we see that going, because really that's where it's heading towards. So talking about power, it's not just a matter about building the systems which are power aware, but also if we start looking at the software that runs on the system, and typically on a large HPC system, it's pretty much taken over with running batch jobs, right? So one of the things that we're doing is instrumenting the job scheduler and the provisioning tools, which is XCAT, and we'll talk about XCAT a bit later on. But when the job actually gets scheduled, Load Leveler will actually contact the provisioning and management system, which is capable. By the way, XCAT's open source, so you can actually download it and tinker with it yourself. so load leveler will go in and ask XCAD at the end of the job and say, hey, how much energy did that job use? How fast were the fans spinning? How hot did the chip get? And it will actually use metrics to figure out, based on, you can actually submit the job and say, I've got a certain quality of service, I need to finish this job by a certain time. And it will actually figure out if your job would have been significantly impacted if it actually changed the clock speed on the servers that it was running on. So potentially, when they've run this, they've actually found that they can get around about between 5 and 10% saving on power for only 2 to 5% change in the job output. So you're at least getting something back. It's not huge, but it's still significant enough to work on. The other way, of course, is to actually design more efficient hardware. So actually design servers. So instead of being deep servers, if you look at our iDataplex racks, which is like x86 clusters, and we'll have a picture of one later on, the actual modules that go into that, the servers, are designed, they're half depth, which means that the fans don't have to push the air as far. So we can actually put these servers in a shallow rack. The fans are reduced, and also because of the fact that we are putting potentially two chassis into a single 2U server space, is that the fans can be bigger, and so therefore they're also more efficient at running. And typically you see that a standard 1U servers go between 18 and 82 watts, and just for the fans in the iDataplex go between 6 and 33. So it does help with these systems. And the iDataplex, if you look at the couple of lists for supercomputers, there's top 500, which gives you basically the floating point ranking of different systems, and also the Green 500. So if you look at green500.org, you'll actually see all the computers ranked by how much performance you can get out per watt of energy that you put into the computer. And so iDataplex is up at the top of the x86 systems, and that's just using these the current technology, which is basically fans, air, and then normally we actually have a water-cooled rear door on that system. So you run chilled air through the rear door, and that typically will take sort of between 80 to 110% of the heat out. So it can actually, if you've got the right volume and temperature of water, it can actually cool the room instead of heating the room up. Of course, you have to pump energy in to get the chillers to work, but anyway. So this is a research project that IBM's working on at the moment, and it's doing water jacket, and those of you who've been looking at the people who do water cooling in their home servers will be familiar with the principle. But this is designed so that it can actually be so that the nodes can actually be placed, or the servers can be placed into the racks and quick connected into a water supply at the back. And the water is taken directly through a jacket straight onto the CPU. So it gets good cooling. There's also, you'll see here, the memory chips are also cooled. And I'm not sure about what else they've decided to cool at the moment. I have heard rumours that they were trying to actually cool adapters by putting cold plates near them, but I don't know. So there's probably still going to be an amount of residual heat that gets taken out by air. Now this is where you start to get real energy savings, because if you're not having to chill the water, you typically use sort of 20 to 50% more energy than you're putting into your computers to actually cool your computer room, even if you're using a rear door with cold water. So this means that you don't have to have chiller plants. If you have got 20 degree to 40 degrees Celsius water coming in, it's sufficient to cool these chips down, because if you ever look at your BIOS or your system monitoring on your own machine, you'll see that you'll be sitting at 60, 80, 90 degrees. So from a processor point of view, 40 degree cools as well as 30. Yeah, sorry, question.
You mentioned the merits of water cooling over, for example, fan air cooling. Water cooling is actually theoretically a lot better in terms of carbon impact, because you can run a chiller off of solar power or geothermal, any kind of heat source can be used to drive a chiller, meaning that you can effectively make your cold water locally with renewable sources, whereas electricity is almost always generated away from where you are, which means you get transmission path loss, and the electricity generation is almost always, carbon ineffective. So
yeah, I agree. I think
it's great because it's a lot more flexible.
Yep. So the comment was about chilling water using other energy forms rather than just electricity, which is true, because I used to be at the beach shack my parents used to own. We had a kerosene fridge, and it ran off. Actually, it was a gas fridge. Sorry, it ran off. They had one which was kerosene and one which was gas, and you could actually light it, and the actual heat from the flame would cool the fridge. So that absolutely backs up what you say, is that the energy, you've got a choice of energy sources. They don't have to be highly refined sources of energy like electricity, which is potentially wasteful. So in terms of what IBM's doing, I've touched on a couple of the x86 sort of products that we have, but we also have a couple of others. So we have this is our deep computing roadmap. So unlike most vendors who are just doing Intel x86, we also recognise that there are problems out there which are not well solved by Intel processors, or that can actually be solved better using processors that we design. And so really there's the power set of platforms. There's our Linux x86 clusters, which the previous to the iDataplex and the water-cooled ones were x86. Although the new Power 7s are also water-cooled, and then we have the Blue Gene series, and as well as that, we recognise the fact that there will be accelerators, in other words, vector processors and multi-core off-board from the point of a CPU, so accelerators will be important, and they may either be off-board or they may be on-board on the chip. So we see, like with the latest Power 7, it actually has a 4-way vector processing unit, so you can actually do 8 floating point units per cycle. So you can do 4 multiplies 4 adds per cycle. So if you feed that correctly, it's a pretty fast processor, and in fact, core for core, it'll go between 4 and 10 times the speed of an Intel core for particular workloads. So there are other workloads where it doesn't do as well, but for things like Fourier transforms, it'll run at up to 10 times the speed if you're using the maths libraries that IBM has hand-tuned for matrix manipulation. And so really, I think I've got, so I'll go through the different platforms. Really, the power machines, they run either Linux or AIX, and you saw the power machine running, Watson was running Linux. The real key to these servers is the fact they've got that massive memory bandwidth, which means that you don't become memory starved as you're trying to do your computation. And also the per core performance is very high because we have high clock speeds on those cores. And of course, for the HPC area, it's also very dense packaging and very fast interconnects, and we're talking about hundreds of gigabytes a second is the network that's running in between these server nodes, and it's designed to scale to really massive levels, and we'll show you an example in a second. Then we have, so really this is probably about reasonably close in energy efficiency to an Intel platform, except with those advantages that some workloads are going to run really, really well that you can't run as well on Intel processors. You've got, and by the way, the Linux Technology Centre in Australia, we actually have a bunch of Linux hackers who are kernel hackers, and who, like Anton Blanchard, and they're actually working on the PowerPC kernel for Linux, so that they do that development here in Australia, in Canberra. So the other platforms that we have, and you'll notice all of them say Linux. So we have a Blue Gene, and a Blue Gene is really a Linux cluster. So under the covers of a Blue Gene are, we'll see a picture of it, but a large number of PowerPC server nodes, and each of those server nodes runs a cut-down kernel, which has all of its function shipping for I/O, etc. The things that give you kernel jitter and stuff like that that disrupt your workflow on a large system, they've all been basically outsourced out to separate nodes which run a full Linux system. From a software point of view, still looks to application software exactly like a standard Linux system, because the functions are just sent to somebody else to do across the network. The Blue Gene, if we have a look at the sort of performance that you get per out of these systems, you get roughly sort of around about 500 megaflops per watt per kilowatt out of these systems. Blue Gene, you're currently getting around about that same order, but the next generation is going to be significantly higher. And I can tell you that, well, it's actually 1,700. So you're looking at about 3 times more energy efficient to do the same amount of calculations. Now the drawback is that the cores on this run individually slower. So you have to have a job that can be parallelized to 3 or 4 times the number of cores, compared with a fast performing core like so per thread performance on a power platform or a traditional Intel x86 style platform. So they're really the two, if you like, proprietary technologies, and they both run Linux and they're both power based. And then we have x86 clusters, and we have x86 clusters, and we support both standard x86 clusters and also x86 clusters with GPUs. And in the iDataplex, that server node, you can actually either put 2 1U servers in, or you can put 1 server in, and there's like a daughter card that plugs onto it, and you can put 2 GPUs onto each of those. And then you have your choice of connecting via InfiniBand or 10 gig E or whatever, whatever rocks your boat. And a couple of examples of systems that, well, this one I've worked on. So this is in Melbourne, and it's Victorian Life Sciences Initiative, and this is the stage 1 system, which is Blue Gene P, and that's 14 teraflops per frame, and the new Blue Gene Q is 200 teraflops per frame. So massive increase in performance between the previous generation and the new generation that's coming. Yeah, sorry, James. Yeah.
The parallelogram. What's in the last one and the first one?
Okay, so the question is about that end parallelogram. What happens is it's actually the way it's built is you've got a frame, you've got a slanty end which slants the other way, which is the air intake, and then between the frames you've got basically a spacer which has a separator, so the air comes up, through, and up and out the top. Now there's also, for larger systems, there was also a water-cooled option which put a radiator in the middle, so it didn't blow out the top, but the end one would always have a vent up at the end. So although it does look like the crawler out of Star Wars, it is actually a purpose. Yeah, no. So that's like. I think it looks quite funky. I think it looks nice. So here we've got on the left-hand side, you can see the management consoles. You can see the InfiniBand switch, the blue switch there. Next to it, there's at the end of the front set of racks, there's an iDataplex rack, and that's got 84 nodes in that rack, and they're Nehalem nodes, InfiniBand, so nothing particularly spectacular in there. All the rear doors are water cooled. The Blue Gene isn't water cooled. In the middle we've got IBM's rebadged DDN disk subsystem. Back right hand corner is the tape library with LTO4s in it. And then you've got the CDU, which is a chiller distribution unit, and that's designed to keep the water temperature and flow rates correct on the rear doors so that you don't get condensation on them. And then you see a UPS towards the right. So that's stage 1. The idea behind this was that it was really to actually get people used to scaling their code up. So we had two racks of Blue Gene, so 28 teraflops of processing capacity, and people would land their code on a they take it from their 2 or 3 servers, land it on the iDataplex, get their scaling issues worked out with their applications, and then they'd port it across to the Blue Gene and get it running if the code wasn't already running on the Blue Gene. So codes like NAMD, etc., are already running on the Blue Gene, so well known and ported. And that's what the Blue Gene looks like inside. You have these little basically single card computers. You have 32 of those in basically in a drawer. Each rack has 32 drawers, and so you end up with 1,024. And on the current system, that's 4,096 cores per rack, and then you just keep bolting the racks together. And I think the maximum is 96 racks, so it's it scales very large and has a 3D network on this one, the main communications link, 3D torus, and each of the links is capable of, so you've got 6 links and each one of them is capable of about 0.5 gigabyte a second. So you end up with, 12 links, 0.5 gigabyte a second, you end up with 6 gigabytes a second total throughput into the torus per node. So, and that torus scales up to the full machine, and it's very low latency, although I can't remember the exact latency figures at the moment. And then the next Blue Gene, the Blue Gene Q systems, which, as I said, this is public information. It's 20 petaflops, 96 racks, 6 megawatts of power, and 1.6 million cores, all operational. And one of the areas that you wouldn't expect that you have to spend a lot of time and energy on is error tracking, error logging, management of hardware, and also then being able to actually keep track of both hardware that's been down to the level of serial numbers for each of these nodes, because what you don't want is bad nodes to be put back into the system. So really, there's a lot of effort was put into creating a database which is used to track all the system hardware right down to firmware levels, microcode levels, the part numbers, the serial numbers of the parts, the serial numbers of everything in there, and making sure that that the system can track down failing components so they can be replaced reliably. Because one of the issues is, and I know that in your large Chinese supercomputer system, which was based on GPUs, they actually had quite a few problems reportedly on when they were actually configuring the system, because some of the BIOSes, some of the firmware, some of the chip versions were slightly different, and they were having problems with that. And so that's another thing that comes out of in the US is called the PERCS initiative, and please don't ask me what it stands for. But basically the high-end computing platform for the US government.
What sort of failure rate would you have on these nodes?
Oh, okay, so the question is failure rate on the nodes. About 100 times less than you have on a standard Intel processor is the failure rate on the nodes.
Which means, given the number of nodes in there,
you still get failures.
Fail about as often as a PC does.
If you get lots, yeah. So that's
in real terms, probably last
not real often, but
yeah.
Occasionally it happens. Yeah.
Yep. And certainly be an issue if you're running one large job that was using all of it, it'd be an issue. But if it's smaller jobs where you just have to run again or go back to your last checkpoint and roll it forward.
Would you typically do the same calculation on multiple nodes just for the purpose of error checking? Or?
No, you don't. So the question was about doing the calculation multiple times to do error checking. No, because the systems are designed, they're reliable in terms of knowing when they fail. There's a lot of the power chip is actually dedicated to error correction and error detection circuitry. So it is actually pretty good at
what proportion, approximately, of your processing capacity is actually error checking as opposed to doing the original?
Yeah, at one stage, I know the chips it was like 5 or 10% of the chip surface, of the chip area, was dedicated to error registers, where you could actually, like if there was an error reported, it would actually snap a copy of all the registers and actually log it to a hardware management, a separate processor that was running hardware management. So I'm not sure on the blue jeans how much is kept in there, but you do have service nodes which do error tracking. So I'm guessing that it's still the hardware's still in there. So, and the Q has actually other interesting things which I can't really talk about at the moment because it's still not officially released, but there's actually significant changes to deal with things like transient errors and recoverable errors in the code, and making sure that you can actually survive them rather than having to take them and fail the node. Which, as density goes up, it becomes more and more likely that you're going to hit those things. So this is the NCSA site, otherwise known as Blue Waters, which is in the nicely named Champaign, Illinois. And it's the middle of Illinois, about 2 hours out of Chicago. And I was sort of fortunate enough to go there and be taken on a tour through it. And it's quite a large building, as you can see. It's got a bottom floor, which is a plant. Then it has a 2-metre raised floor on which the servers are placed. And this facility is, not only is it a large compute facility, but it's also a very efficient one with a PUE. I don't know if you know what that means. It basically means that for 1.1 to 1.2 means that for every watt you put in to drive the computers, you're only using between 0.1 and 0.2 watts to actually heat and cool the system. So that's basically the wasted energy that wasn't wasted in the computer, if you like, as heat. And so a really interesting facility. Yeah, as I said, on the top floor, it's quite massive. Yeah, it certainly was an interesting thing to see. Now, this system is running Power 7 nodes. And the way that they decide on Power 7 nodes was they're running Power 7 and Linux, primarily because it's quite easy to port from an Intel Linux system onto a Power system. Basically, recompiling works quite well. You don't have to make structural changes to the code, and because you're running Power 7 and the performance per core is higher, you actually get a shrinkage of your parallelization problem rather than making it worse as you would with the Blue Gene. So if you like, this is the way to get easy, fast, high memory bandwidth, high I/O rate system, and that's still reasonably energy efficient and it's easy to port to. Whereas the Blue Gene is very energy efficient, but it's a bit harder to port your code because you have to do more work on getting your parallelization right, and the architecture is a little bit different. You have to be a bit more aware of the topology of the network, etc. So if you went in scale of 1 to 10, where 10 is difficult and 1 is easy, porting to this is sort of like a 1 to 2, maybe 3 if you're going to recode your hand tune your code to actually use some of the facilities like the vector. And then if you look at the next one, Blue Gene's probably 4, 5, that sort of order of magnitude to port code to. And GPUs are really much more difficult because it's a complete rethink of your application from the beginning. So they're really sort of at the 6, 7 scale because you can't just take your code and move it there. So that sort of gives you an idea. And so each of the different technologies has their pluses and minuses, and it really depends on what you're going to run on it and what your priorities are. For these guys, power's not a big priority. We're going, guys, how can you afford to drive this with, get this, 20 megawatts is the nominal input power to this facility. Like it's massive. It's a 10 petaflop system, 10 to 15 depending on how you measure. And they're running 20 megawatts into this facility. Okay, how can you afford it? And they said, oh, it's easy. We've got hydro and we've got nuclear power plants just down the road. So if you live next to a nuclear power plant, you're probably not as worried about power. But if you're living, out in WA, or you're putting a computer system out into the middle of nowhere, you're probably going to be willing to spend a bit more time on hand tuning your code to gain some power back, so you don't have to buy two massive diesel generators. You can just get by with one instead. So they're the sort of trade-offs that you make when you're designing these systems as to what type of servers you choose. And so this is what the Blue Waters guys said. What they wanted was maximum core performance, so you don't have to worry about scalability as much. A very high bandwidth interconnect. So that there are a lot of applications like weather and climate simulations where you slice up your atmosphere, or even like reservoir simulation, you'll slice it up into cells, and those cells, once you've done your computation in the cell, you actually have to hand over the data that's on the border to another processor that's computing the data for the next cell. Same thing with computational fluid dynamics, right? So there's a lot of memory, a lot of node-to-node communication or thread-to-thread communication. So as well as so you want something that lets you move that data quickly if you're going to have to be doing it a lot, and you also want large, fast memory so you don't get memory strangled. And at the IVEC talk today, they're saying that you know, with some of the codes that they've seen, the Intel servers can only get to about 20% of CPU before they run out of memory bandwidth. But that's not always true. As I said, it depends on the code. And obviously you want this thing to be reliable, and you want it to have a really fast I/O system. So you've got that sort of hierarchy of bandwidth as you move from your I/O into the system through the different levels of cache and main memory right into the processor. This system you're talking about. The order of, well, it's over 1 terabyte a second file system. So it's a single file system that will be capable of reading and writing at over 1 terabyte a second. So this is really huge. Yeah. So it's yeah. So if we transit from that into file systems, so the file system that we're running there is GPFS, and now the GPFS is a parallel file system, which means that if you're one client machine, you can actually talk to multiple servers at a time and stream I/O in and out to multiple servers. It can also support locking across multiple servers. So even if you've got one file, if you've got multiple clients which are all trying to access different parts of the file, the locking protocols are such that they'll have minimal interference with one another. So it's really designed to scale out to incredibly large levels. The other thing that is built into GPFS is basically a tiering structure which allows you to define within a single directory namespace that some of the files are going to land on different classes of disks. So one type of file might land on 15k RPM SAS drives, whereas some other types of files may land on 2 terabyte SATA disks, and then be migrated automatically to and from tape drives, and also migrated between the classes of disk automatically as stuff's aged, right, as it's used and not used.
That was what the Sandwich controller was doing, wasn't it, about 5 years ago?
The SVC, no, SVC does something a bit different. SVC is basically virtualizing block devices, so you can slam a whole heap of disk behind, and it just looks like one device with one set of LUNs, and you can put new devices in, and it will migrate data across. You're thinking of storage tank,
yes.
SANFS. Well, SANFS, yeah, is sort of similar, but that was at a block level, not like, it wasn't exactly like GPFS. So GPFS is really designed to run on IBM and non-IBM hardware. It'll run on JBOD, or it'll run with DDN, high-end storage at the back end, or anything in between. And basically you can scale it from two servers up to hundreds of servers, and you can do all that stuff online. So basically you get about 2 gigabytes a second per server that you plug in, as long as you've got enough disk throughput behind it to keep the server busy, and enough network to move the data.
That multi-user contention on accessing files, I mean, that sounds awfully like a database. You're doing,
it is sort. Yeah, I know what you're saying. That locking is sort of like a database, but one of the things, and in some ways it is, especially with the fact that when a node goes down, you also have to be able to recover the locks that it was holding, right, or release them nicely. So it's actually. Yeah, a lot of that is a bit like the roll back, roll forward that you see in databases.
There's been a lot of talk in the past about trying to make file systems like that, but it's never really seemed to get anywhere.
IBM actually made a whole system that was based on a database. So if you look at the AS400 or System I, it's sort of interesting bit of technology. It's actually designed by the same person that designed the RISC processor that's in they originally designed RISC processors. So he also designed this system, and basically the System I is a database. There is nothing on the system that is not in a database. So it's a database from end to end, and there are still lots of people who run System I or AS400 applications. So yeah, but yeah, it is interesting, that move towards things being in a database. So anyway, so I just wanted to cover, so that's sort of like the basics of GPFS, and the way it's being used is like in Europe, it's actually used across multiple sites. So not only can you have that performance on site, you can actually have two sites and they can effectively cross-mount each other's files and form one namespace. So that's part of the standard product that we've got out there at the moment, and in fact we've implemented that at the Australian synchrotron. We've got two x86 clusters running GPFS, and one's at Monash and one's at the Australian synchrotron, and they cross-mount their file systems between them. So effectively, from a user point of view, you see one file system, one namespace. No matter where you go, you can actually access your files, security allowing, because you can actually set up barriers so people can't just hop around and hop on another system and use files. But yeah, in Europe, the DISA file system is based on GPFS at each of the sites that actually hosts data, but it builds a layer of caching on top of that, so that you can actually cache at each site. You may have scientists that want to be working on the same data as somebody at another site. They can actually put in a request to cache that data. That data a separate copy will be made, and then the caches will be kept coherent between the two sites, even when you're doing writes. So it's really an extension to GPFS.
Database.
Yeah, and so it's
asynchronous multi-master.
And so what will happen is if you snip the wire between the sites, the people at the slave side, if you like, will continue to be able to see the files, but obviously they can't do any writes. So you can't do any writes until the line gets connected back to the master copy, and that's like a beta test product. As well as that, there's so this is just an illustration of what it looks like. So you've got the various sites, CSC, FZJ, SAR, etc. So they each have their own subdirectory, but the subdirectories are available to everyone that's working between the sites. Another thing that they've done with GPFS as a demonstrator, which was shown off at the Supercomputer Conference last year, is something like the Hadoop file system. And if any of you are aware of HFS, it's not really a file system, but what it allows you to do is put data. Say you've got one large data set, and particularly for text searches and genomics, etc., you have one large data set and you slice it up into bits, and you give each server one slice of the data, and then you let it go off and process. Now, traditionally with Hadoop, you actually had to write a job that would go out and put those bits on the Hadoop file system on the various nodes. With GPFS, they've actually designed it so that you can it still looks like a standard file, and you just basically give it a hint as to how it's going to lay out the files on the various servers. So it's still a full POSIX file system that you can mount and do everything you can with a normal file system. So you don't have those two steps of having to write it to a different type of file system and then read it back again and recreate it. So there's some really sexy stuff that's happening in the file system. And I really like this area. It's sort of something I've always enjoyed, is the tinkering around with file systems. And I promised that I'd talk a bit about XCAT. It's open source, fantastic. Allows you to provision CentOS, SLAES, Red Hat, Fedora, AIX, and Windows Server 2008, if you really want to. It supports management of the hardware, supports updating BIOSes, updating firmware, talking to hardware management servers or service processors or IMMs, integrated management modules that are in your systems. Does automatic discovery and supports being able to deploy these in minutes, right? So you can deploy hundreds of nodes in minutes. So, yeah, sorry, question.
Various IBM systems throughout the last X many years have had various kind of management processes built in.
Yeah.
How far back does XCAT go?
That's a good question. I think it's back to BMC, which is probably about 5 years. XCAT's been around for quite a while, so this is version 2, yeah, it's actually been around for probably 10 years. So if you go back more than 10 years, you're probably in trouble. But I think up to about 10 years, you'll find that XCAT should support it.
And what are the ones before and after BMC, just to give us some context?
I think there's IMM and RSA, RSA and RSA2. I think with the other management. They'll plug in additional management cards that you had to buy, whereas the servers now come standard with a little management server built into it. Yeah. So basically, it also gives you a parallel shell that'll go out and parallel FTP, I think, as well. So yeah, this is now our strategic cluster management system. So it's free. You can go down, download it, tinker with it. If you want to deploy, I'm actually thinking about deploying it at home just to play. Oh, it doesn't show you here. Oh yeah, virtual machines as well. It'll also provision Xen, KVM and VMware onto the systems, and you can provision stateless machines as well, either with swap space and temp space on disk or completely diskless if you so desire. Pretty neat. That's enough on that. And this is sort of the last chart, I think. Yeah. So I guess the thing is that we see that over the years, technical evolution isn't always a straight line. Like as I was saying, it used to be proprietary systems in the supercomputer area, and then it was let's build everything out of commodity components, and we really push the commodity components as far as they can, particularly when it comes to power consumption. And and performance, and we're seeing a lot more a move back towards being able to integrate effectively like Watson, sort of a fit-for-purpose system that's really designed for a particular workload, and this is really the reason why you see IBM out there with multiple offerings in the supercomputer space. So that was it. Any more questions? I just sort of found that interesting. I'll probably rabbit on for another couple of hours, but I think you'd all like to get something to eat and drink.
How much is being done here versus being done in the US?
Okay, so the question was how much is being done here compared with the US? You mean in terms of development, or well, as I said, really pretty much all the hardware development is done US and other countries. So IBM's got research and development labs. I think there are 10 of them now. We opened a research lab here in Australia, but it's really focused on software development and software to support, like the analytics and Smarter Planet and things like that. So, as well as incorporating the collaboratory that we have at VLSCI at Uni of Melbourne. So really, there's not hardware development, but then we have the Linux kernel guys are based here in Australia. Right. Okay. Well,
any of the guys remotely want to ask anything?
I think we had a few questions along the way, so.
I just reckon that file system stuff was cool.
It's pretty neat. Yeah, it's really neat. And I mean, I haven't even talked, like, you can also do stuff like, do things like, you can add nodes and add disk into it and tell it to rebalance, and it will rebalance all of the layout of all the data so that you can get additional performance by striping across a wider amount. It'll do rolling up. You can do rolling upgrades on it, so you can have nodes going up, and then when all of them are up to the latest level, then you trigger if there are any metadata changes between versions, you then trigger a metadata change, and then it does the change. So it's designed to be pretty high. It's designed to be highly available, and you can keep, and scalable. And so yeah, it's.
I ran a GFS on Power 5 about 7-8 years ago, and I'm doing the rolling metadata. Everything's applied, but it's not actually updated the metadata yet, and that's when you sort of go.
Yeah. Oh, I'm hoping it's going to be right. Backups are done. Yes. Okay. Well, I hope you enjoy it, and yeah.
Put your hands together for me. One last quote. Cool. So next month, we haven't got a venue yet we've decided on, but we're supposed to have James Henstridge talking about the Ubuntu One stuff, which I think is Canonical's cloud offering. What, this way?
Yes.
Ah, the light. And as I said at the start, obviously we've got Rusty coming over. If you've got your $20, please see Daniel. And if you'd like to renew memberships, I guess it'll have to be me tonight. Other than that, stay tuned on the Plug mailing list. Thank you everybody for coming along, and thank you again to Indulus and IBM for hosting us here tonight. Tim, you got...
Anyone here who was interested in or has put in one of those, I can't remember who put the entries in now
for the logo? Tim's asking about the logo. So, no, the entries that we've got at the moment I think are from Peter, who might be watching the stream down in Katanning, and from Jason Nichols. So if we can get a couple more ideas from anyone, that would be good. And we'll try and, I guess, get a decision out by the end of the week, maybe?
Yeah, I think we give people a little while to do some tweaking of them if they want.
A little tweaking.
Comments.
Yeah.
But yeah, I think without a doubt we've actually got something to change to now. It's going to be better than what we've got.
Yeah, hopefully better. Cool. All right. Thank you, everyone. We'll kill the stream and get going. Thanks, everyone.